So thank you. Thanks, Jefferson, for the invitation. Where's Jefferson? Okay, he left. Oh, here. Thank you for inviting me, and thank you all for being here. This is work done with Leonardo Della Porta Dornelli, my student. And I'll try to walk you through this subject of, again, neuroscience, neuronal avalanches, and collective oscillations. The broader context is that this is how I see the scenario nowadays. This is theoretical physics after, I don't know how many centuries since Newton. Everything works fine. Everything is kind of well-polished, very well-polished, like a golf course. And this is theoretical neuroscience. You enter a jungle and with a knife, and you cut some fig of and you find a new place, gold mines and stuff, right? So it's very new. And we're trying to understand what to do with so many neurons. And we know how one neuron works. But many neurons, it's complicated. So the background of neuronal avalanche and the critical brain hypothesis, this is how I'm going to introduce the subject. And then I'll talk about this model and how we're trying to answer some basic questions in, I think it's physics, I hope. So in 2003, Beggs and Planks published this very, by now famous paper in Journal of Neuroscience, in which they take slices of the red cortex here, and with 60 electrodes, they measure the local field potentials, and observe these bursts this time, bursts of activity, with a good separation between those events, and hence they term them avalanches because of the separation of time scales between those events. And when you look at these statistics of, you can look at them here again. These bursts of activity, they call an avalanche, and they define the size of an avalanche as the number of active electrodes. And if you ask yourself, what is the typical size, the mean size of these events, what you find out is that the question is wrong because they are power law distributed. And they are power law distributed with an exponent which is well known to physicists. So this is a 3/2 exponent. Okay, before we go into physics, this is very important for neuroscience because it means that questions like typical to biologists, which will be like, what is the mean size of an avalanche? The typical size of an avalanche, the mean plus or minus standard deviation, they are meaningless, right? Because it's a fat tail distribution. And this has a bearing on what a neural code, if there is one, what it could be like. It puts limitations on how it could work. So this is non-trivial scaling variance statistics, as we know, and this exponent is well known in physics. So, by the way, this has been repeated in anesthetized rats and in unanesthetized but resting monkeys. So you see always the same power law with the same exponent. So this fueled this critical brain hypothesis or conjecture, which has been put forward by some people, Dante Calvo, Perbach in the 90s, in the context of self-organized criticality, and some claim even Turing in the 50s. So the idea is that from the dynamical point of view, the brain will be somewhere here, or fluctuating around this point, around some second-order phase transition. What are the control parameters? We don't know. What are the other parameters? We don't know, to be honest. But the fact is that that exponent 3/2 is consistent with some, with a branching process, which is well known for 100-something years. More specifically, if you're a statistical physics enthusiast, you know the directed percolation universality class. In the mean field class, this exponent 3/2 occurs exactly here. So if you take a branching model like this, these are neurons, and they spike, and with some probability they cause another spike in a downstream neuron. If this is subcritical, this is sigma less than 1, the branching ratio less than 1, the activity dies out. If you're supercritical, if you're here, your branching ratio is larger than 1, activity will spread and become self-sustained, stable here. And if you're critical, you are in the verge between the transition between those two scenarios, and here you have non-trivial statistics, as we all know. So the pros of this kind of model, well, it gives you the right exponents as you observe in the slices in neuroscience. So this is exponent for size, this is exponent for duration distribution. And it also gives you a response exponent, it's critical exponent here, with maximum dynamic range, as we showed many, many years ago. So this is good, nice. And essentially, this gives you a theoretical workhorse, a mental image to think about this problem, what's going on, right? This is why it was useful as a model. So this is one marker of criticality that I'm showing you, experimental one. Again, another experiment here, showing you, again, the same power law distribution. And if you tweak the system with chemicals, it can become supercritical. And then someone came up with an index which somehow quantifies how close you are to this critical value. So this is kappa, which I'm going to be showing a lot here. Kappa less than 1 means you have a supercritical distribution like this. And kappa larger than 1, you have a supercritical distribution like this. This is the cumulative distribution function associated to this distribution. Okay. So what is the second one? There's another marker of criticality which appeared in a completely different context. If you look at, for instance, freely behaving rats, it's a completely different system. The animal is behaving as it wishes, and then something else appears. If you measure the same entity, those avalanches here, and you make a time series of those avalanches, then you can study those fluctuations a long time. And I mean the time domain of this phenomenon, if you want. From this time series, you can calculate power spectra and see some kind of 1/f scaling here, which then you can also measure alternatively the same thing. With determinate fluctuation analysis, you observe this root mean square deviations from a linear fit. It scales with some exponent alpha, and we know this is Fourier transform. If the autocorrelation function decays with theta minus gamma, then this beta is 1 minus gamma, and this beta is also 2 alpha minus 1. You know, well, just some scaling, simple calculations actually. And from this, if you see that those alpha values are close to 1, alpha close to 1 means gamma close to 0, which means that you have very, very, very long range time correlations, which then have, again, implications for what the neural code is, or how the brain of this rat is behaving. So people also try to think of this, associate this to memory, for instance, roughly speaking, of course. So this is from an old paper of ours. So you have this different kind of marker of criticality if you associate it with criticality, the fact that, again, at a critical point, you don't have exponentially decaying correlations, but power law decaying correlations. So, by the way, this is also observed in the kind of experiments that Gandhi was describing before. So in large-scale measurements of the human brain as well, like magnetoencephalography or functional magnetic resonance imaging, you also find this kind of long-range time correlation. So if you go back to this theoretical workhorse, the branching process, kind of branching processes, now it fails miserably to explain that phenomenon, because first of all, here separation of time scales between avalanches is imposed by hand. You have an absorbing state, so whenever activity dies, you have to, as the simulator, or you have to start it over again, right? So by definition, you impose separation of time scales, something that does not occur in the natural system, and also you miss these time correlations completely between consecutive avalanches because you don't control this anymore. So to the best of my knowledge, we don't have a model for that, or we didn't until this paper came out. So this POIL model came out in 2012 in the Journal of Neuroscience, and it consists of I'll go quickly, but I mean, the model, because it's very complicated. So the model has inhibitory and excitatory neurons. It's a very small network for physics, right? 50 by 50, with some local connectivity, 7 by 7. You have excitation, you have inhibition, and all kinds of connection, respecting the ratio that you see in the cortex. And so you have these parameters. And the control parameters of the model is the fraction of excitatory synapses and the fraction of inhibitory synapses. You control excitation and inhibition. It's a very complicated model with probabilistic spiking and lots of local integrations. What matters for us here is the following. I mean, forget about those numbers, just a lot of numbers. The only one that matters for me, and for, I mean, maybe for us physicists, is the fact that you have a constant background input here with some constant Poisson rate, if you want, which therefore prevents the system from having an absorbing state. There's no absorbing state. And therefore, if you don't have an absorbing state, what is the phase transition? If there is one, right? So we are away from the theoretical workhorse that I referred to before. And what is it that they observe? Just simulations here. Essentially what they observe is that as you increase the excitation and inhibition ratio here, somehow collective oscillations start to appear. And these collective, then all those parameters were adjusted so that these oscillations look like what you observe in a magnetic encephalography from a human brain at rest. So essentially, as you go, so this is parameter space, inhibitory connectivity, and excitatory connectivity. As you go from here to here, this is the power peak of the power spectrum here. Essentially, as you go from blue to red, you go from blue to red here, and you see a peak in the power spectrum appearing. And interestingly, so this will be the transition of sorts, some oscillations starting to emerge. And interestingly, the DFA exponent becomes 1 precisely at the transition here, transition point. So these are nice, because this looks like something we see in the data. And what about avalanches? It's very hard to talk about avalanche in this model because it has no separation of time, I mean, of time scales precisely. What they do is they artificially introduce some kind of threshold here, some half of median activity. And once you do this, you define an avalanche as something that goes above this threshold, and then you have another avalanche here. So you have the avalanche duration, the avalanche size here, and you have, again, a power law distribution with the exponent which is observed in the data. Again, with kappa larger than 1 if you are supercritical, less than 1 if you are supercritical, and approximately 1 at the critical point. And again, if you look at the transition occurs, you have a transition line here of sorts. Again, measured by this parameter kappa. Nice. What about avalanches and long-range time correlations? So if you go, again, back to those markers of criticality, they observe this DFA exponents close to 1. They observe the power law side distribution of avalanches, and they're consistent with each other. This is kind of amazing in the sense that if you look here, this is the red line here is when alpha is close to 1, and this blue line here is where kappa is close to 1, and they cross here at the right point. So, wow. I was very impressed, but a little bit concerned. So this is all very nice. But there are many questions. For instance, so these markers of criticality like DFA, like power spectrum, they don't depend on any threshold that you impose. But this one does. So what if you change the threshold? I mean, are results consistent? Results robust. This is question number 1. Question number 2. This is a 2-dimensional model, or is it 50 by 50? Come on. In physics, you don't publish in physical review with 50 by 50, right? I think, if I'm a referee. So, and this exponent here is a mean field exponent, right? It's a mean field exponent. So, I mean, how come? What gives, right? So what happens if we just fix the local connectivity and increase system size? I have avalanche exponents compatible with D equal 2, which is what I hope, if this makes sense at all. And so I'm going to try to ask those questions. I'm trying to look at this threshold, see how robust the results are by studying the probability distribution of this avalanche as defined by all this area here, or the area just above the threshold, and change this parameter gamma, which changes the threshold. What happens if we fix a local connectivity, increase system size? So I fix this little square here, and increase the big square. Are exponents for this P of S compatible with D equal 2? The exponents for mean field and D equal 2 for direct percolation are more or less like this, approximately these. And what about avalanche durations that they didn't look at in this paper? And can we define another parameter? Are results consistent? DFA, kappa, blah, 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 etc. So let's see. Let's look at this first question. So what we are seeing here is different lines correspond to different values of the threshold. And this is a kappa heat map in parameter space. So yellow here means kappa close to 1, which means that the probability distribution of sizes are close to the power law predicted by mean field theory. And you see that as you increase the threshold, results remain more or less consistent. I mean, it looks like there's some kind of transition here, as used by this criterion, for the activity above the threshold, but not for the whole activity. Okay. What happens if we fix the local connectivity and increase system size? Again, going down here, increasing system size, and you see, if you look at different measurements, for instance, this is the frequency of the peak of the spectrum of the Fourier transform. You see here the power of the spectrum. You see some kind of transition here, more or less in the same region where the DFA exponent approaches 1, more or less. I mean, but somehow results remain as increased system size. That's the important message here. So it looks to be somewhat robust as far as their assessment of the phase transition are concerned. So I was more intrigued by this, actually, by this dimensionality. So what we did is, the idea is the following. You have, if the system is in the mean field or 2D class, for the same simulation, you do the following. You compute this kappa, assuming G equal 2, so the kappa for this probability distribution. And you also calculate the kappa for this one, and see if you have a transition in which of them, or you compare those things. When you do this, it's very, oops, sorry. So it's very strange because you see both for the 2D distribution and for the mean field distribution, you seem to have a transition, which is very strange. Which is very strange. So we wanted to look at more detail in those green region here. So what we do for those for this green region, look, it's the same simulations here and here. The only difference is how you're measuring how far you are from a power law. This is from a power law for 2D for the 2D exponent. This is from a power law for the mean field exponent. So we wanted to do something a little more kosher, if you want, using maximum likelihood estimator with the power law with the cutoff here. And if you look again at this green region, what you find is that this is the maximum likelihood estimator, so the larger the better. You see, if you look at those two arrows here, and look at the predicted exponent by the mean field, by the maximum likelihood estimator, you see that this one here is close to 1.27 or something, which is the 2D exponent, and this one here is close to 1.5, which is mean field exponent. So these are the two. The same data can be fitted by different critical exponents if you're in different regions of parameter space, which is very strange. According to this estimator here, this guy, the red one, wins, which is good. This is the 2D case. Okay? Wins by a little, I don't know. You could repeat the same kind of game for the avalanche duration, which also has a predicted exponent. Again, you do the same thing for 2D. This is more or less exponent. and this is the exponent for the mean field, and you play the same game again. You look at parameter space, you look in detail, you try some maximum likelihood estimator, and again, you see, if you walk around parameter space, you go from one exponent which is close to mean field, another exponent which is close to 2D. Actually, it's nice because in this case, the mean field doesn't work so well. The mean field exponent is 2, and the best we can get is 1.74. Good. So 2D wins a little bit. Can I define another parameter? Are results consistent? The model is so complicated that I cannot use the variables to define, the microscopic variables to define another parameter because they vary discontinuously. It's very strange. So we just try to do what the experimentalist would do. The experimentalist would only have access to, for instance, the Fourier spectrum of the global activity. This is a typical thing that they have. So if you take the Fourier spectrum, you just kind of find some, for instance, the area of this peak divided by some area here. Let's call it phi. So just measure how large your local peak is. And if you do this, you do obtain this putative order parameter as a function of one of the control parameters. You do find something which looks like a little bit like a phase transition with an exponent beta, which controls how this thing departs from here, which doesn't look like much like the 2D exponent. Very strange. I don't know. You can see how this, again, in orange is the order parameter. It departs here, and close to here, not exactly here, the DFA exponent peaks at close to 1. It peaks a little bit to the right here. So this seems to be some kind of consistency among those measurements. And again, these scatter plots a bit ugly, but please bear with me. Here I'm changing the thresholds, and here I'm comparing two-dimensional and mean field results, and mean field predictions, so to speak. And what we're seeing here is that the kappa, the predictor for two-dimensional universality class of a power law, is compatible with alpha close to 1. So this is consistency around that region. It also works well for 2D, for the duration distribution. This is size distribution, this is duration distribution. Here you also find a better fit for mean field. So the consistency here seems to be better for this for the size distribution with the alpha. Also mean field seems to work better here. So it's very, you can think of this as numerically investigating this problem, which I didn't see theoretically addressed. So let me go back to this, to the concluding remarks, to see if I can pose the questions that are still plaguing this field. So we take their model, which has many, many details, we increase the system size and find that their main results hold. We find that the probability distribution for size and duration can be fit by values in the direct percolation universality class for d equals 2, but also for mean field in some regions. It's very strange. We have started sketching this order parameter, which departs from the critical point with the critical exponent close to the DP value for d equals 2, but not quite. And then some open questions which we are working on right now is that, so we're looking for a hopefully much simpler model than this one, which is very complicated, that can qualitatively reproduce these results while allowing for a proper scaling analysis, because this is just too messy. And then the question, a more basic one, is this: to which extent, if any, can the relation between the onset of oscillations and then effective directed percolation-like transition be formally established. To the extent that any model is always an effective model, right? This should be obvious to us. But can we transition from one model to another and connect those two things? It's really, I don't know. But I would love to hear if you have something to say. So thank you very much. Oh.